Lab 2. Lab 2. Lab 3. No, you're on Lab 3 now. You're handing in Lab 2 today. Lab 3. Any questions about Lab 3? Anybody got a drum sound out yet? Yeah? How many nodes?
15 by 15.
Can you get a good sound out?
I think so, yeah.
Were any perplexities that came out that...
Yeah, I mean, after the sound, there's like some noise that continues. It's like really low volume, but when we look at it like on the scope, it looks like it shouldn't be there.
Kind of, is it sort of a nyang, 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 nyang kind of sound, or...
It's just like white noise, but it's really soft. You can barely hear it unless you turn the volume up.
Uh-huh.
But it's not there when you hit the reset button, so I don't...
So you hit the reset button, it's completely gone,
Yeah.
and then you strike a drum, and then the drum decays, and then it's back again.
Yeah.
Okay. What I'm going to hypothesize is that you're looking at a limit cycle noise. At some point, no matter how precise your calculations are, you're running out of accuracy at low amplitudes. And excuse me. And what's happening is that the arithmetic is settling into some little tiny feedback loop which is generating a constant output because the damping is no longer effective. My guess. How many bits are you carrying? 18-bit arithmetic. So it would be interesting to plot the ratio of the peak drum sound to the noise at the end and see if the ratio is about 18 bits. Because you can hear more than that, right? You can hear a larger dynamic range than 18 to 2 to the 18th. It would be interesting to see if that ratio makes sense or whether I'm just completely full of it. This could be a few more bits higher than 18 bits because you could imagine that you're doing a subtraction eta delta t over 2, 1 minus eta delta t over 2. If eta is fairly small, or eta delta t over 2 is fairly small, then you're going to, and the amplitude is decreasing, so the u that you're multiplying by is fairly small, that you're going to run out of significant digits. This is not going to be significantly different than 1 times u after a certain point, which depends on both u and eta. So the ratio might be significantly bigger than 18 bits. It could be 12 bits even. Any other? So 15 by 15. Yeah, tunable and all that kind of stuff. You can change the tone. Yeah, cool. Anybody else got it running? Anybody else? Yeah, got a node running? More than one node? Did you do?
It doesn't sound like the drum though.
What's it sound like?
It sounds. Well, I mean, it sounds like a percussion, but the register is really off. So I think that's just because we're using a square drum head.
Well, they're right. Square drums do sound different than round drums, and depends on where you hit them and a lot of other things. Are you using? So are you using a single point state machine? Just a yeah.
Yeah. We're assuming you only strike at the center.
Right. Okay. Anybody tried the symmetry thing? Joe, you're doing that, right? Yeah. Yeah. Well, I need to talk about that a little more because I think I did that badly last time. I think you got it right and I got it wrong last time. And that was that if you're simulating a drum and you want to just simulate 1/4 of it and then reflect the results into the other quadrants, what you need to do, say along this boundary, so on this side you're computing and on this side you're not computing, then on the boundary the result has to be symmetric around the boundary. That means that if you compute this point, you have to have another point over here that you are not computing, but merely copying to this location and then using to update this point on the next cycle. I think I said it right this time. Yeah. So you're computing this point, they're free to move, but this point is merely a copy across of the point you're computing here. This enforces symmetry across the boundary, but says nothing about the slope at the boundary. Because this configuration is allowed, this configuration is allowed, or in fact, this configuration is allowed, as long as it's symmetric around the boundary. Anything else on Lab 3? Comments, questions? All right, well, let's go back to Lab 4. I spent a lovely hour today. It takes a long time to download the Quartus 2 stuff, even with Cornell's pretty fast connection. I think it was about 45 minutes of download time. It was beastly, but I wasn't very careful. I just downloaded everything. You know, the Stratix stuff and all of that. So I probably did a fairly stupid download. But after I downloaded Quartus 11, I've been using Quartus 10 on my machine because that's what was already installed. I downloaded Quartus 11 so that I could install the Altera monitor program. I haven't used this before because in years past it was a little simple. It didn't have enough functionality. Now it apparently does. The Altera monitor program allows you to pick up a description file, a .ptf file, which is generated by SOPC builder. So SOPC builder. SOPC builder builds the computer system that you're going to be using. It generates a PTF file which describes the computer system in such a fashion that the Altera monitor program knows what to do with it. Altera monitor program also knows how to compile C, and it knows how to link the hardware abstraction layer, the HAL, hardware abstraction layer, to the C program. So what happens behind the scenes here is that the PTF tells Altera monitor program how to generate a C-lib for the computer you just built. So it generates a library of function calls for the computer you just built so that when you use hardware abstraction layer commands, then the compiler can find them and use and compile the C code. There is no editor associated with Altera monitor program. You can use any editor you like to edit the C. And I know there's at least one Emacs junkie in the class, so he will be happy that you can use whatever editor you want. I just use Notepad because I have no taste. And you use Notepad, you tell the monitor program the name of the program, the top level program which is associated with the PTF file, and it does the right thing. In past years, I've had people use the NiosII IDE, Integrated Design Environment. All of my documentation is written for the Nios IDE. I suggest you don't use that. This is vastly harder to set up than the Altera monitor program. Altera monitor program is not yet installed on our machines in there because I didn't ask for it to be installed. You can do it yourself because, of course, you're running as administrator on these machines. So you go to the Altera site, you Google up Altera monitor program, you download the version 11.0 version of this, and you install it. And then you will have it until somebody logs out. And then you'll have to install it again. So, if you put it on your Z drive, if you put the EXE, if you download the EXE onto your Z drive, then all you have to do when you log in is double click it, install it again, and you'll be ready to go. It's a little crude. I did have a little trouble on the lab systems convincing the Altera monitor program that Quartus 2 was installed. So I'm not sure how that's going to work. You can fall back to the IDE. That's why I gave you an extra week. But you probably want to try and get that going. Worked beautifully on my desk machine. I have to try and get it running in the lab. Took an old project, which I will show you in a couple of minutes, compiled, reran SOPC builder, reran Quartus 2, cranked open the Altera monitor program, and had a running C program in about 2 minutes. It was really easy. And the documentation is pretty good too. So, let's talk about a specific example of a program, a C program, but to do that we have to specify what computer it's running on, because now we get to build our own computer every time. In a way that's slightly easier than, maybe not easier than using Pancake, but with somewhat more flexibility. So in SOPC Builder, and it's got a nice GUI, but in the end what you're going to do is you're going to add a CPU, you're going to add an SDRAM 0 driver. For this example, I added an LCD driver, hardware driver, a JTAG UART, an output port called out0, another one called out1, an input port 0, and then an in1 underscore 8-bit. This was to remind me that this is actually a 32-bit input and this is an 8-bit input. And a timer. So this is all done using a point-and-click kind of interface. You have a drag-down menu of different kinds of bus modules you can add. And there's a nice graphic that says that this is going to be on that the CPU is the bus master and SDRAM is going to be on the data bus and on the program bus, but the LCD is going to only be on the program bus, or on the data bus rather, and the outputs are only on the data bus. So you specify a system like this by dragging and dropping these various units on there, and in some cases right-clicking them and saying how many bits wide each of the I/O ports should be. The usual kind of Windows interface. You can set the properties of an object by right-clicking on it. You can set how much cache you want in the CPU and the exception address and the base address and various other things of that sort. You really do need to read the SOPC tutorial, however. Read the SOPC tutorial. It'll show you how to add all this stuff. Once you add all this stuff, you press the generate button, and then you sit back and look at YouTube for 4 or 5 minutes while this thing generates the Verilog for you. And one of the things you're going to specify in the CPU is a name. The name then becomes the name of a .v file. So it's going to generate a Verilog file with the name of the CPU. This Verilog file is an interface file. It's gigantic. But if you search for this name within this file, you will find it someplace down in the middle of the file with a specification of the order of I/O parameters. So down in the middle of this file someplace will be some ugly, unbelievable piece of code that says something like NiosII clock reset underscore n, which means it's reset low. Then something in port to the in 0. Oh my God. In port to the in 1, but however the order in which these appear in the I/O list is completely random with regard to what order you put them in SOPC Builder. Therefore, you have to copy this out into your high-level module so that you can generate the interface to the CPU. There is no substitute. Further, and it goes on and on. The ZS address from the SDRAM 0 and so on. It's so bad that the only way I could figure out how to do it was to find an example and copy it. So there's lots of examples online on the 5760 web page because I think it's incomprehensible otherwise. But the one thing that is useful is that the names over here get duplicated up here. So this would actually be in1 underscore 8-bit. So you get the template for connection from the name.v file, where name is the name of the CPU. But then, of course, you have to write a top-level module which connects this CPU that you've just built to the outside world. So now you write a top-level module that is going to connect the LEDs and the LCD and what other peripherals you want to the CPU. In this particular case, I wrote I can't even remember why I wanted to do this at the time, but I wanted to run a direct digital synthesis unit from the CPU, and I wanted the direct digital synthesis unit to play a scale. So it's going to start at middle C and go to C above middle C, putting out sine waves through the VGA port. Well, it turns out the VGA port can be disabled and turned into a 10-bit A to D to A converter. So this is not completely insane, it's just strange. So rather than using the audio codec, in this case I was just using the video port as an audio port. And because I was having trouble getting the CPU to run, I also, as part of the hardware, downloaded a direct readout from the switches to the hexadecimal display so that I could make sure that the hardware was downloading even if the CPU, even if the software didn't run right. So there is an LCD on the board. It is connected to the CPU. There is a way of turning off the video connection so that you can use the VGA as a general DAC. So let me just lay out the hardware first, and then we'll do the software, the C program that runs on the computer we've just built. So there's the usual interface junk, and I'm not going to write that, the inputs and outputs to the board. That's all very straightforward. We do, however, need some registers, including a 32-bit direct digital synthesis accumulator. You all familiar with direct digital synthesis? If I say DDS accumulator, you know what I mean? Yes? No? No? Okay. So direct digital synthesis is a way of using table lookup to produce arbitrary shaped waveforms. And in this case, we're going to be using it to produce a sine wave. So we need a way of indexing a sine table. And the way this is done almost universally is to use a long accumulator, in this case a 32-bit accumulator, and we're going to use the top 8 bits as an index into a table. So we're going to address a table from the top 8 bits. The output of this table then is going to go directly to a 10-bit DAC, and then thus out into the world as a voltage. And the 32-bit accumulator is fed back on itself through an adder This is clocked at some rate. And the other input to the adder is going to be some sort of phase increment. So we're going to treat this 32-bit number as the phase of a rotating phaser. So this is going to be a phase accumulator, and the phase increment is going to give us how much we advance the phase of the phaser on each time step. Okay? If we have a 32-bit if we have a 32-bit counter being clocked at some rate clock, then it overflows this often. All right? Times, well, yes.
The table contains data for each phase?
The table contains amplitude data for each of 256 different phases. Yes, exactly. It includes the amplitude data for 256 different phases. If we were to increment if we were to increment at if we were to increment, if the phase increment was set to 1, so that we're incrementing this by unity every time, then the system will overflow this often. So this has units of time, right? Because this is counts per second. We flip this up, it's got time. So this is 1 over a frequency. So the lowest frequency that we can generate then is clock divided by 2 to the 32. If we were to increment the phase more rapidly, if we were to increment by 2 every time, rather than 1, then we would generate 2f naught. So the frequency that we can generate then is given by the clock divided by 2 to the 32 times the phase increment. So if we want to generate this frequency, then we can set the phase increment to f times 2 to the 32 over the clock. So if we want to generate middle C, which is 261 and a fraction hertz, so middle C is about 260, actually it's closer to 262 hertz. We would plug in 262 here, crank this out, and we would get the phase increment. For the case where we have a clock frequency of 50 megahertz, then this formula reduces to f times 85.8 0.8994 hertz. This is for a 50 megahertz clock. So what we're going to do in the program then is that one of these outputs, 32, is going to be a 32-bit output from the CPU, which is going to set the phase increment. Therefore, the software running on the CPU will be able to determine the frequency which is put out through the VGA port. So direct digital synthesis is very nice because for the cost of a 32-bit register and an adder, 32-bit adder, and a fairly modest table, 10 bits by 256 entries, we can generate very precise sine waves. And I've written the table for this. I've also written 16-bit 2's complement tables so that you can output sine waves through the audio DAC. Those are all online in various places. So, but we need to write then the Verilog, the high-level module, has to include a direct digital synthesis unit, the table, and an interface to the hardware, the DAC hardware, as well as the LEDs. Once we have that, then we can write the software that runs on the CPU, which is going to include a timer interrupt to get the length of the notes and a scale factor from the switches so that we can set the octave that we want to produce. So there's lots of levels of abstraction here. We're going to generate a CPU, then we're going to embed the CPU within a Verilog program, and then we're going to download software to the CPU which will interact directly with the hardware in Verilog. Messy. So we need this register 31 down to 0 of DDS accumulator. We need a wire of 31 down to 0 of DDS increment, and also out 1. And in this case, I generated 2 signals in quadrature because I was playing around. So we need 2 wires of sine out and cosine out. It turns out the name I used for this particular Nios was Big Nios. And I think the reason I did that was that the first one used on-chip memory and was little. It didn't do much except it ran an interrupt service routine and blinked a light. the first two things you always do with a new microcontroller when you're trying to figure out how the damn thing works is you write an interrupt service routine and blink an LED. If you can write an interrupt service routine and blink an LED, then you know how the interrupt structure works and you know how the I/O structure works, and that's almost always the hardest thing when you're messing with a new microcontroller. But then after that I realized that the little microcontroller with the on-chip memory couldn't support a printf, and so I wrote a big one that uses SD-RAM and other stuff. That's why big Nios here. And we're just going to call this NiosII, so that's going to be the name associated with it. And I wrote this in a style which I would not use again. So the example online, by the way, this is all online. The example online uses parameters which are given in order. Clock 50, reset, actually no, it's key 0. And I would not use this notation again. I would use dot notation. So you have dot reset. This should really read dot reset in parentheses key 0. You should write it like that because every time you run SOPC Builder, the order of the parameters can change. And you will go mad trying to figure out why the program won't load anymore. And the reason it won't load is because one of the I/O ports was in the wrong order, and so the Verilog mapped it to the SD-RAM port. And if you can't get to SD-RAM, you can't load the program. And so the only message you will get is load failed. Not why. No reason to think that anything is wrong. It'll just say load failed. Great. Could be the clock's not running. Could be that I forgot to define the I/O pins. If you forget to include the assign file in the project, then the processor is deaf, dumb, and blind. It can't get to SD-RAM, and therefore the load fails. Great. Why doesn't it tell you that? I don't know. It could be that you have the wrong parameter order. I found so many ways to make it fail. I think I put a debug section in Lab 4 so that you could tick them off one by one until you found out what was wrong. So, but this style is the bad old style. Switch, key, DDS, increment, out 1. Then the LCD requires 4 signals. LCD enable. These might look familiar. Have any of you ever programmed an LCD interface in a low-level language? Then you'll recognize these immediately. Every Hitachi clone LCD works exactly the same way. It has an enable line, a control line, a read-write line, and 4 data lines or 8 data lines, depending on how you've set it up. I don't actually know whether this is 4 or 8. LCD, because that's been abstracted too far down the list of worries. So there's 4 LCD control lines, and then there are 10 dynamic RAM, DRAM control lines. DRAM, ADDR, something very obscure, curly brackets, DRAM underscore BA1 and DRAM underscore BA0, curly brackets, and a whole bunch more of stuff for the dynamic RAM. I'm not going to write it all out. There's a whole bunch of parameters. Again, I've never particularly figured them out. I just put them in the right order. And they work. So once you've done this, then you've instantiated a big NIOS with local name NiosII as part of your code, but you also need to instantiate a phase lock loop of type SDRAM phase lock loop. We're going to call this -3 nanoseconds. And to understand this and to get an example of it, read the SDRAM tutorial. The input is clock 50, and the output is DRAM clock. Oh, but since I wrote this example worked fine. Actually, it worked fine today. They must have fixed it. In version 9, this worked, where the CPU clock is clock 50, the SDRAM clock is retarded 3 nanoseconds. In version 10, it did not work because the internal definition of the phase lock loop was changed. And so you had to output another value here, which was clock 50. In other words, it was the same frequency and the same phase as the input, but because it went through the phase lock loop, it got shifted by the same amount that the DRAM clock got shifted. And so you had to use here, instead of clock 50, you had to use clock 50 coming out of the phase lock loop. I don't think you're going to run into it this time, because I think they fixed it in version 11. The effect will be, can't load the program. Then we have to write the logic for the direct digital synthesis. And that's really easy. DDS accumulator gets DDS accumulator plus DDS increment. End. Then we need to hook up the tables And I abstracted this in such a fashion that we could use the sync-ROM module. Remember that from lecture 2? Sync-ROM. I'll probably rewrite it. We're going to use a abstract out the constants in such a way that Quartus 2 understands that it should use an M4K block for the table. Sine table, clock 50, DDS, accumulator, bits 31 down to 24, those being the high order 8 bits, and then sine out. And we need another sync-ROM. Cosine table, clock 50, DDS accumulator 31 through 24, but we want to add to that 8-tick hex 40. That causes a phase shift of 90 degrees. Cosine out. And if this overflows, that's okay, because the map is circular. Then all we have to do is to assign VGA underscore red. Remember that? That's the red output channel. We'll just make this sine out VGA green be cosine out. But we do have to also assign a couple of values to disable the VGA timing. We're going to set VGA sync equal to 1. Assign VGA blank equal to 1. And assign VGA clock to be clock 50. And we have to assign LCD on equal 1, and then end module. So that's the top level module that connects the CPU to the direct digital synthesis unit, to the switches, to the keys, to SD-RAM, and the LCD. So now all we have to do is write the software that runs on the CPU, because right now we have a system which, if implemented, you download this to the board, it does nothing. It sits there and stares at you. So we have to have some software to run on it now. Any questions? Okay, yes?
In the CPU clock, there are limitations.
How fast?
How fast?
Yes, but the main limitation seems to be from SD-RAM, which is only good to about 18 nanoseconds. So you can't run it much faster than 50 megahertz. If you go to a on-chip memory, you can run quite a lot faster.
Okay, so this is like you need to worry about synchronizing between the DAC and the hardware that's generating the sample in the same way that you do with the audio.
Oh, good question. It's because the DAC is a DC DAC. The DAC is completely asynchronous. When you load a value into the DAC, that voltage appears nanoseconds later. The bandwidth of the DAC is at least 150 megahertz. So the value you ram in here more or less instantaneously becomes the output value because there's no clock on it. Well, there is a clock, but it virtually doesn't matter for this. Okay, anything else? Well, let's go to the lab.